Yeah, hello everyone. Today we have a session on quantum
Right.
science and technology, and very a few a one-line description of quantum science is the science behind the smallest particles. I think you can use your audio to let me know there are people from class ninth or there are people from 10th, 11th, 12th as well.
Ma'am, we have from 9 to 12 here.
Okay, thank you. Just
Yes,
I just
yes, yes.
wanted to know because I there are few technical terms that class 11th and 12th will be able to understand pretty well as compared to ninth and 10th. So as you
Okay.
know, I am currently at UIMP and doing my masters, and this is my email address. I'll tell you later as well. A little about me, as she already introduced me, so I don't think I need it. But I have a little slide that she don't know yet. So I also did my minor in cognitive science, which is a brain science, and I'm also an intern at NTech right now. We are a writing intern. I'm working as a content creator there, and I also volunteer for climate change. And I love gardening, reading, singing, uh, and many other things. So let's just keep this aside. Welcome to the world of quantum science. Are you all ready? Just give me a yes. That would be great.
Yes.
Cool. It's not going to be boring, trust me. This one slide seems like a lot of English, but it's pretty easy. Okay? So, it is a science I told you that we talk about tiny particles, but this is not where we end. Quantum science begins at the tiny particles. So, we just don't talk about electron, proton, neutron. We also talk about their energies and what is going on, like their interaction, light matter interaction, and behavior of the matter, like what is the behavior of an electron, behavior of a photon. You might think they are very tiny particles, why do we need to study about them? But please remember, these are the fundamentals of our science. Without electron we cannot exist, this whole universe cannot. So it is very important that we know about these tiny particles that we just think that we can take granted for. No, we cannot. One of the key factors why quantum mechanics came into the picture was that people were doing experiments and they figured out that light is not just a particle, is not just a wave, but light is particle and wave both. I think class 12th can relate to it and they might know about this, but class ninth and 10th, they might not know. They will think that they studied light as a wave, like you can see things because of light, but light is also a particle in form of photons, and light is also a wave. When you talk about optics, you see a lot of light going on here to there. So classical mechanics is a very realistic subject that you can see around yourself, like this laptop that I'm using, the class you are sitting in, the fan you might have, the AC you have. This is all classical mechanics. You can see it, you can touch it, you can feel it, you can use it everywhere. But where comes the quantum mechanics? For quantum mechanics, you have to go deep. Even a microscopical study that we biology people do using microscope cells, etc. Quantum mechanics is much smaller than a cell. So think about it. It's very small, very small. Now let's go to the experiment that made quantum mechanics what it is today, the double slit experiment. This is a very famous experiment, and I think class 12th would have studied it, but if not, don't worry. It's a very, for me, it's a very cute experiment because it gives the existence of quantum mechanics in picture. Like people used to think that electron is, goes into the nuclear physics, because in nuclear physics we talk about electron, proton, atoms, protons, and things like that, molecules, etc., etc. But through this experiment, we got to know that light is not just a particle and it's not just a wave, it's both. So, light can exhibit a dual nature. That is a very important property of light, and it is very amazing, fascinating. That was the whole reason why I, choose to go into quantum mechanics. So, let's do a fun thing. I have a YouTube video, not mine, but Professor David. You might have heard of his few videos. You might have seen his videos. Let me see if it comes. A bit technical. Yeah, here it is. The audio is not important. I want. you to see the image that he will show. It's a wonderful experiment.
In beyond. The
This part. Here you see that light is coming from. There are two slits, one here, and light is coming as a wave. This is an experiment where you see that okay, light is coming as a wave. It forms this kind of a pattern, and you see this pattern. This front view is what is
recorded.
so you see in this experiment we see light as a wave, and now we got this pattern. Okay, now this second image you see here, this here the thing is that you are choosing electrons which are particles, and you are putting them one by one in this slide, and even then they make this kind of pattern which is very similar to the old pattern that you see in the wave picture. This picture and that electron picture, it's basically the same. Even though they are particles and waves, they are making the same pattern. That is the question, because it cannot happen if only if electron was just a particle and light was just a wave. It could not happen. It is just not possible. So therefore there comes in picture the scientist who is can anyone name him, by the way? It's written in the slide, although it's fine. It's Louis de Broglie. So he was the one who first came and said that it is not just that light has a dual nature, it is that every one of us, each particle in this universe, has this dual nature. And this was a game changer because people used to think that only small particles have it, maybe only light has dual nature, maybe only electron has a dual nature. What's going on? It was so confusing until he came and he gave this very simple formulas which tell us that not just electron, not just photon, not just light, each particle that exists in this universe has a dual nature. Each particle has a wave associated it and a particle. And now you may say, oh, I am a human, I don't have a particle, I don't have a wave associated with me. Well, why don't you we see our wave nature? Like, why can't I move around like a wave do? Like, why am I a particle? Why I have a mass and why can't I move? That is a very good question, and the answer to that is that because we have a larger mass. As you see, electron is a very tiny particle, same goes with photon. They're very small particles, like very small, and therefore their wave nature is extremely large. Because our mass is very small, our mass is very large, like me as a human has a large mass. Same with elephants, same with plants. They have a very large mass, and therefore their wavelength nature is very small. By the way, from here on there comes another physics or another science which talk about the aura, which currently we don't consider a science, so we don't talk about it much, but people talk about this thing. They say that each person has their different aura. Gen Z's or younger generation might relate to it, that people have their own aura. So that aura is nothing but just a wavelength that people have. So I don't want to say that it's a pure science. It's not. We don't consider that as a science, but it's a research topic. People are researching on it, that whether these things, the wavelength associated to human beings are different, how are they different, and things like that. But in quantum mechanics, what we say is that the larger the mass is, the wavelength is small. So we don't see our wavelengths. Okay? Now, I will be talking about two very important quantum phenomena which are very important for ninth students. I especially made the slide so easy for you all to understand because I thought that there will be ninth students only. But because there are 12 kids, it would be good, nice. You will enjoy it. What is a quantum superposition now? You may say that if there is a cat which is dead, so you say, oh, that cat is dead. And then if you see a cat which is playing around as doing fine, you will say the cat is alive. But surprise, surprise. In quantum mechanics, we have this phenomena which is you just read, quantum superposition, where we say that there is a box, and in that box there is a cat, and with that cat there is a radioactive element, and the box is closed. It's a black box. I cannot see what is going on inside. So the cat could be alive or could be dead. So this is a quantum analogy to understand what is quantum superposition. It's a very simple example. I'll give you a brief little experiment. This is a thought experiment. I will name the scientist soon that who thought of this thought experiment, who gave this thought experiment, and it was a wonderful experiment, and people were able to understand that okay, quantum is actually weird. But don't worry, quantum science is a legit science, it's a real science that happens. So this, if you see here in this box, you see a cat which is playing with a butterfly, and this red rectangular thing, just consider it as a button. It's a button, okay? Now this is the radioactive element. The catch is if the cat clicks on this button, then the radioactive element will be, in the picture, and it will basically might kill the cat. But if the cat do not press this button, then this radioactive element would not work. I mean, it's closed. The thing is that until it presses the button, it won't work. So now, if you think, how would you know the cat is alive or dead? Because this is a box, which is a black box. You cannot see what's going on inside. If anybody could just thought about it and tell me the answer, like how would you know if a cat is alive or dead? You cannot see from outside, so you have to either go in or I don't know. Do you think if anybody can just come to the wherever the mic is or wherever the screen is?
Want to
Interact.
interact?
If you want to
Fast,
ask
fast, come
questions,
fast.
you can.
Come fast, come fast. Wait, come.
Anyone, don't
No,
don't
no,
hesitate. Just go ahead, say anything.
The cat is both alive and dead until we can observe,
Yes,
right?
yes.
Yeah.
Which class are you in?
10th, class 10.
Great, great. Nice, nice. Wonderful answer. We have to observe. He put a word which is very important in quantum mechanics. The things we do in science, in quantum mechanics especially, observe. Until you observe it. And how will you observe it? You have to open the box. And once you open the box, then only you can tell if it's alive or if it's dead. Because from outside you cannot see, right? This is quantum mechanics. This is the core of quantum mechanics, is that until you observe. And the amazing thing that happens, let's come back to the double slit experiment. The amazing thing that happens in double slit experiment is that once you observe that the light or the ray or the particle or the wave, whatever you are throwing from the source, whatever is coming, once you observe it now, it shows a classical result. It just changes the result automatically. Once you observe what light is coming from, which slit it is passing from, it changes its outcome, it results. In quantum mechanics, when you observe something, the result changes to the classical answer. For example, in the simple cat experiment, until you open the box, you think it's in quantum sense. You think that cat could be alive or dead. But once you open it, it's a classical result. It will be either alive or it will be either dead. So that is the beauty of quantum mechanics. It really depends on observation. So this is a Schrodinger's cat. It's a very famous cat. In quantum science, we use it a lot in quantum communication, in quantum, research. We use this term a lot. Schrodinger's cat. This is a very famous scientist, Schrodinger's, who is, you can say, pioneers in quantum mechanics, quantum science, and he gave this analogy, and it was wonderful. And the key takeaway is that particles exist in multiple states until measured. So until you measure it, it may exist in multiple states. Okay. And the second amazing phenomena we are going to talk about is something that even Einstein questions. Oh shit, I was about to ask who is the scientist. Can anybody name it? But well, I did. So he said once that about the second phenomena I'm going to talk about, he said about this phenomena is that spooky action at a distance. Honestly, Einstein was not in favor of quantum mechanics. He was always questioning that how can it be possible? How can it be possible? No, quantum mechanics cannot exist. But later we had a scientist had a very famous conference called Solvay Conference, where many big scientists came together and they finally decided that quantum mechanics is a legit science. It's not a pseudoscience. It's not imaginary. It is happening in tiny scale. He called this phenomena spooky action at a distance. Why? Uh, can anybody think that why is he saying like spooky action at a distance? Why is he so concerned about this spooky word? Like, can anybody think or maybe try to answer like why was he so
Anybody wants to answer the question?
yeah provoked about the spooky action? What was he concerned about?
Anybody?
Ma'am, like,
Come fast, come fast. Let's go.
It's okay because Einstein puzzled it. So you can also. It's totally fine to not know or not think about it. You are like, whatever, he said it. Who cares? But it's very important. Come forward.
Probably he felt it was abnormal,
Mm-hmm.
and it was like very like unexplainable.
Yeah. Yeah, true, true. It was unexplainable and even now it
Why?
is.
Well, basic thing is that action at a distance requires some agent.
Hmm.
Action at a distance requires an agent, and here such an agent doesn't exist. That is the whole point. And spookiness, spookiness. Thank you.
Yeah, thank you, sir. Yes, so in the second phenomena that we are talking about, okay, I didn't put it right now. I have another experiment to show you. It's another very thought experiment. Is that let's suppose Alice and Bob met together somewhere and they decided that okay, we have two black boxes now. One black box will be carried out by Bob and one another one will be with Alice. Okay, now Bob opens his black box and he saw a left hand club, right? You can see it, right? Spin up, left hand club. Now he saw that, yeah, he has this, and now he immediately will tell you that Alice has the right one. He don't need to measure anything, he don't need to call Alice, he don't have to tell anything to Alice, but he will know that the right one is with Alice because I have the left one. This is a kind of a correlation between these gloves has, right? In an electron analogy we call it spin up and then spin down. So the thing is that now you understand it quite easily that okay, it's a glove, of course it has to be in pair, so if one has a left, other has to have a right. It's easier to think in classically with this example, but in quantum mechanically Einstein was not able to, neither many of the scientists were not able to, because it is very rare that you have two black boxes, you share two black boxes and they are very distance apart, very distance apart. You open one black box and you will immediately know what is the second black box has, like what is going on in second black box. This is magical, to be honest. Like suppose you have two black boxes, you don't know what's inside, you shared it with one of your friend and you opened a box and you can tell that what your friend has it. So this is a problematic, a little bit problematic. It is because in classical physics we think that look, if I'm calling you from here to from Agra to Karnataka, there has to be some connection, exactly like my phone is connected to some tower and that tower is connected to you, so there is some middle agent, just like Kulkarni sir mentioned, there has to be some agent. But in quantum this entanglement, there is no, like if those two objects are entangled together, if those two boxes are entangled together, you don't need any agent, you can just take these two objects further away, like one at sun, one at earth, one at Mars, doesn't matter the distance, but you will know the outcome once you measure the first one. It is intriguing, if you read more about it you will find that it is a very fundamental and it changes the way we used to think how can we communicate, because this opens up the question that oh, two people are communicating without having a common channel, like how is it possible? So it is a wonderful phenomena and it changes a lot of things about our perception on how the world we think of. These are some real life applications of quantum technologies. The image that you see here, this is a quantum computer. It's not a full image, I will show you later also, but this is kind of how quantum computer looks like. One of the very famous application that currently is so hyped up that you must have heard about it is quantum computing. The second one is quantum communication, and third is quantum sensing. Quantum sensing is the one in which I am working, because it is very close to experiment sites and it's very close to physics. This quantum computing is wonderful for people who love computing and who love physics. And this quantum communication is for those who love, you know, quantum science as well as the communication kind of engineerings. And sensing is for, I would say, anyone can enter to any field. It's just that these applications are major applications that we have in quantum science. Okay. Now for class 9th and 10th, it might be a bit difficult for you to understand, but 11th and 12th will get it. I also try to make it so simple that you will understand it. So what we have, I will not talk a brief about quantum computation so that you know what's going on in quantum computation. Why is it different from classical? Okay. So in classical world, we usually see alive and dead, the quantum superposition concept that I just told you before. In quantum world, we see alive and dead as a one single state. Okay. So in quantum computation, we use this property of quantum superposition to do the computation. Okay, this is very simple, not very simple, but this is basic. Quantum computation very fundamentally depends on the property of quantum superposition. We do use quantum entanglement as well, but superposition is where it gets its power. Quantum computation is revolutionary, of course, because it has those, properties of quantum mechanics. It can use the properties of quantum mechanics and do multiple things and amazing things that classical computers cannot. Okay, there's a table here to make things simpler for you. This is a classical computation way. Okay, we use zero when you must have heard of bits, like we use 0101. There are so many things, like all the classical information that we have today are on these bits only. Okay, for quantum computation we have qubits. Now these qubits are interesting because just like in this image, you see these 0 and 1 is like bits, and this is a qubit. Qubit has the property that it could be 1, 0, or both. So this is very fundamental to quantum computation, that you know about what is a qubit. Now quantum computer, this classical one, this process information linearly. But in quantum computation, we have the power of superposition, and that is why we are able to compute things very fast. For example, you can see this classical computation is now limited by Moore's law, and you know that the chips are getting very small, very small, very small, very small, and now they are coming at the size of quantum world. And because they are coming at the size of quantum world, now it is not possible to make them more smaller, because if you make them more smaller, they will use the property of quantum mechanics, and that way you won't be able to make classical computers. You have to come to the regime of quantum computation. Okay, and quantum computation solve problems in exponentially faster way. We will see next applications like how they are solving exponentially faster. I don't go much into the mathematical details, but I'll tell you few algorithms, okay, that works. The examples, your laptop, smartphones. For quantum computation, there are quantum simulators right now that we use more often, and then there are quantum computers. Now, you know, take note that I have written future quantum computers, which literally means that the current quantum computers that we have are not the ones that we need. Okay, we are trying to make quantum computers more advanced, more perfect, so that we can use them in real time. The quantum computers we have right now are not very efficient in their working. Okay, now I talked about exponential speed up, right? I have to tell you why. Okay, so these are two algorithms which changed the game: Shor's algorithm and Grover's algorithm. And if I remember right, we recently even got the Nobel Prize in 2022 to the scientists who worked in quantum computing, basically. So they got the Nobel Prize, and Peter Shor was the one who first made the Shor's algorithm, which he wrote a whole research paper. He talked about how we can use quantum computation to break encryptions. Now, class 11th and 12th, you may note this, that encryption is the thing which is keeping our world together right now. All the bank details, all the information that the governments have, all the critical and sensitive information are encrypted in numerical form. Okay, those are prime numbers. Actually, those are very big prime numbers, and to factor prime number out, it's difficult. If you use a classical computer to do that, it will take years to factor out the prime number, so it's very tough. Okay, But what happens is that Shaw's proved that Mr. Shaw, Dr. Shaw proved that you can use quantum algorithms to encrypt decrypt those encryptions using quantum computer and these algorithms. So after Shaw, there comes another algorithm, which is Grover's algorithm. This algorithm also works for the breaking the encryptions. So these are very important algorithms, and currently, let me say this very honestly, that the quantum computers we have right now, they are not at the level that we can use these algorithms and encrypt, you know decrypt, sorry. So we need quantum computers who can actually work. And you might say that why she keeps telling that we don't have quantum computers. We do have what's the problem? Why are they not ideal? What is the problem? The problem is with noise. There is a lot of noise which is in quantum computers. Because of that noise, we are not able to come to this conclusion that we can do these algorithms on those computers. So we are still working, scientists are still working on it. Now, the another advantage we have is that beyond classical limits. Actually, the thing is that the problems that a classical computer can solve in like years, like hundreds of years, 20 years, 10 years, that problem can be solved just in few minutes using quantum computer, because quantum computer has those property I told you about, quantum entanglement and superposition, and there's few other properties. And now you say, okay, so which company is investing? Here you go. This Willow is a recent quantum chip that was made by Google this year, I think only. They're claiming that they can do some calculation in 5 minutes, which will take a supercomputer to do these many years. Now, the reality is that it is theoretically proven, not practically. We need quantum computers to do that. And therefore, if you see, these are other properties, these are other applications, sorry. These are other applications that we use. Even ISRO is interested in it, quantum communication. They are also trying to make it in space. Like they made one satellite in the space and one observatory, and they started the communication between them using quantum channels. Okay, so even big companies like ISRO, NASA, these are those scientific institutes. But big companies like Google, IBM, Microsoft, these are all investing in quantum. Okay, and these are other applications of quantum. Like it has applications in molecular interaction, which comes into the uh, medicine regime, right? In cryptography, I told you optimization is where the business comes. Okay, so when you go to so people who might have commerce, they might understand, or people who might know about this, it's okay. Quantum science is interdisciplinary. Please remember, not only science people, but finance people and other people are also working on it. Okay, so logistic problems and supply chains problems are also solved using quantum computers. Okay, it's a little quiz. I was just to talk a brief about it. Actually, it's fine. You can just go and see what other quantum applications are, because I don't want your discovery or your interest in quantum computing ends here in this talk. After this, I also want you go to search on internet to see things how people are doing it. These are three basic questions I put in, just so I know that you are listening to me. So the first question is, who said spooky action at a distance? Anybody can answer. You may speak loud also. Doesn't matter. It's just exactly cool. Why do we need quantum technologies? Just one example, one application you liked. I think everyone like a different
No,
application.
one of you, take the mic. Take the mic from there.
Mic.
One of you.
Mic. One example each.
Stronger encryption.
Yeah, good. That's a very important one. That's the immediate property application that we are working on. And name of any quantum computer.
There. Willow.
Yeah, good. That's a quantum chip, but that's you can call it a quantum computer. I also put few other names so that you go ahead and see how it's going on. So this is IBM quantum chip. Okay, it's called hummingbird. There are so many other chips. They are all quantum computers basically. In a okay, I have another slide. So these are the names, and Willow is right. Of course, it is right. I only told you one because I have wanted to have some multiple one here. So they are. I used it because in 2024 I didn't work much on quantum computing. I worked on quantum sensing. So yeah, use that chip, their quantum computing for that whole coding thing, Qiskit. I haven't mentioned it here. Although I have this. So this is what I was talking about when I said that they have quantum computers, but it's just that we need to improve on quantum computers. Look, the Falcon, which released in 2019, had 27 qubits, which is a great thing, to be honest. If you think that 27 qubits are very small, actually no. Even with these 27 qubits, there is a lot noise going on, and because of that noise we are not able to use the full property of these 27 qubits. This is where the problem lies, because we have so much noisy quantum computers. And now you must be wondering, why so noise? Well, these are tiny particles, but they are very noisy. And there is one another field in quantum science which works on error correction, which means that because of the noise, that it creates a lot of error in the answer. So you have to then again solve that error and check that error. So these are the quantum computers. This is a roadmap by IBM only, although Google has one also, and Microsoft also. But these are the quantum computers they have, I think.
Excuse me, ma'am.
Yes, go ahead.
I wanted to ask a question.
Mm-hmm.
What do you mean by that the computers are not able to function properly because of noise? Like, what does noise refer to here?
Yeah, I'll come to that. Um, okay, let's answer your question first. This is a quantum computer, you see. There is a refrigerator. What does refrigerator do is reduce the temperature. Now you see, my laptop is working. What is the temperature in Agra right now? It might be 30 degree maybe. Yeah, 30 degree. Let's say 30 degrees centigrade. Now my laptop is working very cool, very fine, no problem with my laptop except some hangs. That's all. But a quantum computer needs, what temperature to operate on? It needs a temperature of 0 Kelvin. You know what does that mean? What is a 0 Kelvin? Can anybody name the other name we have for 0 Kelvin?
Absolute zero, ma'am.
Exactly. Think about it. And do you think we have absolute zero temperature right now in any lab?
No, ma'am.
Exactly, we don't have it. So, unfortunately, because we don't have that perfect temperature, we work on quantum computers with 1 or 2 or 3 Kelvin. That is also very minimum temperature, you might say. But it's not perfect. So, because it's not perfect, we don't have the ideal quantum computer that we want because of the temperature, because of other things as well. Because you see these golden lines, this outside golden lines, these are the coolants, okay. So to reduce the temperature here, they I think they put some gases to make this very cool, very low temperature at the quantum chips. This small quantum chip is what is basically what is the motherboard of this quantum computer. They put this here, okay, and they make the temperature very low, try to make it very low, very low, very low, but we still have not come to the 0 Kelvin, which is absolute zero. That is where the noise creates, because we don't have this perfect system where there are these things, these apparatus even make noises. Even this, this atmosphere you see outside, this create noise. Have you heard of anything like how to make semiconducting chips? Have you heard of
No, ma'am.
vapors? No, no, okay, no problem. I'll explain you. It's simple. When you make your computer motherboard or the computer chip, like Intel chips you have in your laptops, you have a room which is what do we say? Vacuum. We make those chips in a vacuum, because even a tiny particle of hydrogen or a tiny particle of nitrogen can create a lot of trouble making these chips. You know why Apple laptops are expensive? Because Apple phones and laptops, they are one of my professor told me this, I think in back in 1 year ago. She was teaching a semiconductor physics, which is how you make these computers, these electronic devices. Is that these Apple ones are so expensive because when they see any impurity in their chips or in their phone, they discard the whole sample, they discard the whole phone. And these discarded phone then are used in those company which you get few cheap phones. Okay, so the cheap phone that you buy of 6,000, 7,000, those phone, you know why they are cheap? They are cheap because of the manufacturing. They are cheap because the chips that they use are a little bit defective, not in a very huge sense defective, but they are not as good as the expensive phones chip. The rate in the phone market comes not just because of your camera quality or the storage, it comes from the chips that are inside your phone. So I have a phone which is not very costly, but I have a laptop which is costly. So the only difference between those are the micro chips that we have inside them. Similarly, in this quantum computer, if there has to be no defects, like no other gas, no other molecule, no other atom, no other electron, nothing in this chamber. And do you think it's possible? Can you answer? Do you think it's possible to have no electron in a room?
No, ma'am.
Exactly, that is the problem. We don't have this much clean rooms. They are called clean rooms actually. Even when you go inside that room, you have to have a white full cover up. Just like doctors go to surgery and they do the surgery, they have full cover up. Similarly, in these clean rooms, when you make the chip, you have a whole dress for it. Your eyes are fill with the glass. You wear glass, you wear all the white clothes, so that there is no single dirt that goes into that room. And because of these ideal conditions, we are not still able to come to that ideal quantum computer that we want. So these are few impurities, irregularities that we have. And you see, this is whole quantum computer. This whole is not a quantum computer. This chip is just important quantum computer that we have. This chip is the one which works. This golden setup, these are here some few there are few circuits that we use for quantum computation. But other than that, these golden lines, that the big setup is just so that we keep the temperature close to 0 Kelvin, which is not 0 Kelvin, by the way. It's 1 Kelvin, 3 Kelvin, around that Kelvin. Okay, that is where the noise comes in. And therefore I was telling you that these qubits that we have, if you think that okay, there are 1,000 qubits in Condor, this is so great. Well, it's not that great, because these qubits, the more qubits we have, the more noise we have. Getting the point?
Yes, ma'am.
Yeah.
Okay.
Yeah, I hope it answers your question, right?
Yeah.
That is the problem. There is nothing like ideal gas. So we have to work with real gases. Now, yeah, this I just told you what it is. I was just talking about that this is a whole refrigerator setup, and this is quantum chip is just this tiny chip, you know. And then we have key takeaways from the slide. I summarized the whole slide in this, I think, 5 points, so that you take away these points to your home and think about it a lot and think that, can I do something crazy with quantum computers? You have the access, you may read about it, but please remember one thing I wanted to tell to kids who are in 9th or 10th, in even 11th and 12th. It is very important that you know the fundamentals. Quantum mechanics is a field which is very different from classical one, but it doesn't mean that you don't study classical mechanics. It is very important for you to study proper fundamental physics. Okay, so don't skip that, thinking that this is. I just wanted to give for further reading. I worked with this company. I'm an intern there, and we do write blogs for people, for students, basically. Uh, so this is a section where I wanted to tell you that there is a physics section where we have quantum mechanics, and there we have lot of vlogs related to quantum mechanics. And because we write these vlog in simpler language, so you understand, So therefore, I just wanted to tell you that don't end here, okay? Go and explore. And plus, I don't want to tell you that go and study quantum mechanics. What I want to tell you is go explore what you like. It could be anything, but you know what? Quantum will find a way to come to you, because in future we are working on very different fields, okay? It gives application in not just physics, it gives application in chemistry, biology, commerce, finances, and communication. A lot of engineering thing happens, a lot of commerce thing happen. And one important thing I always forget to mention, I also worked with quantum music. And you might wonder what is quantum music. So quantum music is another very quantum science and art subject where you create music using quantum computing. So there is a lot of application going on in quantum computing. It's not just science. We have gone beyond science now. So I think this is all for the talk. Hope you have a nice talk. And if you have any questions, please go ahead. Shoot me with questions. I love to answer. And that's my email address, by the way. If you have any question related to anything, I love to do science communication. I love to tell students about what is science, what is quantum. So please, if you have any
Right.
question, you can ask now.